Welcome to Introduction to Instrumentation. My name is Anna.
And I'm Nigel. Together, we will be your narrators for this series of introductory videos. After successfully finishing this course, you will be able to define and explain instrumentation is and what it does. Define commonly used instrumentation industry terms. Explain how pressure is measured, and explain how some instruments are used to measure and control it. Calibrate a pressure transmitter and demonstrate its operation. Explain different methods of measuring temperature, and demonstrate the use or resistance temperature detectors and thermocouples. So why are we here? Most of you are probably thinking, I want to be an electrician. Why do I care about something called instrumentation? Look at the world around us and you can see the forces of nature at work. Clouds and storms, waves and tides, scorching deserts, frozen continents, and gravity holding everything together. What if we could measure those forces? What if we could convert pressure, temperature, flow, or level into an electrical signal? And what if we could use that signal to control machinery and make a process respond? That is why we are here. Instrumentation allows us to sense what is happening in the physical world, communicate that information to a control system, and then put machinery, and some of those natural forces, to useful work. We have been doing this for millennia, although rather crudely at first. Think about the natural cycles surrounding us. The Earth's rotation gives us day and night, and our earliest reference for measuring time. The sun heats the land, oceans, and atmosphere unevenly, producing changes in temperature, pressure, humidity, and weather. The Earth's tilted orbit gives us the seasons. And the gravitational pull of our old friend, the moon, helps produce the tides. Long before electrical instruments existed, people observed these changing conditions and used them to decide when to travel, plant, harvest, hunt, and seek shelter. Measurement has always affected our lives, and, in many cases, our survival as a species. Let's go back and look at some of the earliest measuring instruments people created.
Civilizations began to grow when people learned to cultivate crops and produce a dependable food supply. But farming required something new, the ability to predict what nature would do next. People noticed that their shadows changed length and direction as the day progressed. That observation eventually led to the sundial and a practical way of measuring time. They also noticed that the sun rose and set in slightly different places throughout the year. Its height in the sky changed with the seasons, and after roughly 365 days, the pattern repeated. By tracking that pattern, people developed calendars. Time was no longer something that simply passed. It was something that could be measured, recorded, and used.
Some days were hot. Others were cold. Hot weather wilted crops. Cold weather froze lakes and fishing holes. People could feel the difference, but feeling wasn't measurement. About 2,000 years ago, Greek engineers experimented with devices that showed how air and liquids responded to heating and cooling. Around 1593, Galileo developed an improved thermoscope. It could show that the temperature was changing, but it did not provide a standardized numerical measurement. Later instruments added scales and became increasingly consistent and accurate. The device we now call a Galileo thermometer was developed later, using principles associated with Galileo's work. Early liquid thermometers still had limitations. Water could freeze, and instruments did not always agree with one another. In 1714, Daniel Gabriel Fahrenheit developed a practical, sealed mercury in glass thermometer. Mercury responded consistently, and remained liquid throughout ordinary environmental temperatures. Each generation improved the instrument. Hot and cold had become conditions that could be measured, compared, and recorded.
Here's something we take for granted. Our planet's atmosphere doesn't feel like anything, and for a very long time, people didn't believe air had any weight at all. How do you measure the weight of air? Here is something we normally take for granted. The atmosphere doesn't feel as though it weighs anything. We can't see it, and most of the time we can't feel it, except when it moves as wind. So how do you weigh something you can't see and can barely feel? For centuries, people did not understand that the atmosphere was pressing down on everything around them. In the 1600s, Evangelista Torricelli demonstrated that the atmosphere exerted pressure. His mercury barometer balanced the weight of a column of mercury against the pressure of the surrounding air. The mercury moved because the atmospheric pressure changed. For the first time, the invisible weight of the atmosphere could be observed and measured. As barometers improved, people learned to associate changing air pressure with changing weather. Once again, measurement allowed us to turn something invisible into useful information. With every new invention, we discovered that we needed more information. James Watt's improvements made the steam engine far more practical and efficient, helping drive the Industrial Revolution. But steam was both powerful and dangerous. If pressure was not properly monitored and controlled, boilers and pressurized equipment could fail catastrophically. Industry therefore needed reliable pressure instruments. The development of instruments such as the burden tube pressure gauge allowed operators to see what was happening inside equipment that could not be safely opened or inspected while operating. That same need continues today. As we ask automation to perform more complicated and powerful tasks, we need more sensors to monitor the machinery and the processes being controlled. Industrial progress is driven not only by better machines, but by better instruments that allow us to understand, control, and protect those machines.
These early instruments represented an enormous improvement, but they only provided information. The pressure gauge could tell an operator that steam pressure was rising. It could not decide whether the pressure was too high, and it could not adjust the process. The operator had to read the gauge, decide what the indication meant, and then manually reduce the fire, adjust a valve, or take some other corrective action. The instrument measured. The operator decided. The operator's hands controlled the process. In other words, the feedback loop already existed, but a human being completed it. The next major step was to replace some of that human observation and decision-making with automatic control.
By the late 1800s, instruments were beginning to do more than display information. In 1883, Warren Johnson patented an electric room thermostat called the electric telethermoscope. A bimetallic sensing element moved as the room temperature changed. That movement opened or closed an electrical circuit and signaled the building custodian. The instrument sensed the temperature. The electrical contact communicated the condition. But the custodian still had to adjust the furnace damper manually. The gauge had become a switch, and the measurement had become an electrical signal. Johnson continued developing the idea. By 1895, his pneumatic temperature control system could use a temperature-sensing element to change an air pressure signal. That signal operated valves and dampers, controlling the building's heating system. The instrument sensed the temperature. The controller responded to the signal. The valve or damper changed the process. The resulting temperature was then measured again. The human operator was no longer required to complete every cycle. The feedback loop had become automatic. This simple ideas, and hundreds more lead to the lifestyle we enjoy today. Millions of sensors, measuring almost everything. All of these sensors communicate with controllers that take action and ensure a process is automatically adjusted without for constant human intervention.
So what is instrumentation? Instrumentation tells us what is happening.
And process control determines what should happen next.
Instrumentation is hiding in plain sight in our homes. Right now, your home is safer because instrumentation keeps us clean with hot water, keeps our food safe and store it longer, and allows us to control the cooking process, keeps us warm or cool by controlling our home's environment.
Whether is making steel or assembling automobiles, cutting cloth or cooking food, modern industrial processes cannot function without proper instrumentation and maintenance.
Because processes can become dangerous long before the danger is visible to the people operating them. Consider these events: 1. Walkerton, town water contamination, inadequate monitoring and reporting. 2. Bhopal gas disaster, failed or disabled safeguards, poor maintenance and ignored warnings. 3. 3 Mile Island partial meltdown, inadequate and misleading instrument information. 4. Chernobyl nuclear disaster, unsafe design, procedures and operating decisions. 5. Great Boston molasses flood, poor design and testing, followed by visible warnings that were ignored. These disasters did not all have the same cause, but each demonstrates the importance of obtaining accurate information, understanding what that information means and acting on it before conditions become catastrophic. 1. Instrumentation tells us what the process is doing. 2. Maintenance ensures that information can be trusted. 3. Training allows people to interpret it. 4. Procedures determine what happens next. Without all four, preventable problems can become preventable disasters. The Walkerton inquiry explicitly concluded that proper instrumentation and monitoring could have prevented that tragedy.
We will return to the Boston molasses flood throughout this course, not because one missing instrument caused the disaster, but because nearly every condition involved will appear somewhere in our lessons. We will examine hydrostatic pressure and head. We will compare the specific gravity of molasses with water and calculate why the pressure was much greater near the bottom of the tank than at the top. We will study temperature, thermal expansion, and the effect weather can have on a process. We will consider the tank's leaking seams, visible warnings that people had noticed long before the failure. Local children reportedly collected the leaking molasses as a treat. We will also examine the inadequate design, construction and testing of the tank, along with the absence of useful pressure and temperature monitoring. No single condition tells the complete story. The disaster occurred when an unsafe vessel, changing process conditions, ignored warnings, and an unusual combination of events all came together. Some consequences were predictable. Others were not. Instrumentation helps us understand those conditions before they combine into something catastrophic.
In our next video, we will be going over some more key terms you will be using throughout this course. Until then, thanks for watching. Leave a comment if you have a question you want answered.